A dead galaxy is not empty. That is the first mistake most people make. When we hear the word dead, we imagine silence. We imagine a place where nothing moves, nothing grows, and nothing waits. But in space, death does not mean emptiness. A dead galaxy can still contain hundreds of billions of stars. It can still hold ancient star clusters older than our sun. It can still hide white dwarfs, neutron stars, black holes, clouds of hot gas, invisible dark matter, and sometimes a sleeping monster in the center with a mass millions or billions of times heavier than the sun. From far away, it may look calm. No blue glow from young stars. No bright stellar nurseries. No colorful clouds giving birth to new suns. Just an old red system, quiet and cold, drifting through the universe like a burned-out city after the lights went off. But when astronomers point Hubble, ALMA, Chandra, and the James Webb Space Telescope at these dead galaxies, the story changes. They do not find nothing. They find fossils. They find violence. They find clues from the early universe. And sometimes they find evidence that galaxies may have lived fast, burned through their fuel, and died far earlier than our models expected. The universe has graveyards, but those graveyards are not empty. They are hiding the history of how galaxies are born, how they grow, how they starve, and how they die. And the strangest part is this. Some dead galaxies may not be completely dead. They may only be waiting. To understand what is hiding inside them, we need to start with what a galaxy really is. A galaxy is not just a beautiful spiral in a telescope image. It is a massive gravitational system. It contains stars, gas, dust, planets, stellar corpses, black holes, and a huge invisible halo of dark matter holding the entire structure together. Our own Milky Way is one galaxy. It contains hundreds of billions of stars. It has spiral arms full of gas and dust. It has old stars in its halo. It has globular clusters orbiting like ancient swarms. And at its center sits Sagittarius A star, a supermassive black hole about 4 million times the mass of the sun. The Milky Way is still alive because it still forms stars. Not very fast compared with some galaxies, but it still has cold gas. Cold gas is the raw material of star birth. When huge clouds of cold hydrogen collapse under gravity, they fragment into dense pockets. Those pockets heat up. Pressure builds. Fusion begins. A new star is born. A living galaxy keeps doing this. It takes gas, turns it into stars, recycles material through supernovae, and keeps glowing with different generations of stars. Young stars are often blue and bright. They are massive, hot, violent, and short-lived. Old stars are redder, cooler, and longer-lived. So when astronomers look at a galaxy and see strong blue light, glowing gas, and active star-forming regions, they know that galaxy is still producing new stars. But when they see a galaxy dominated by old red stars with very little cold gas and almost no star formation, they call it quiescent, or in simpler words, dead. This does not mean every star inside it is dead. It means the galaxy has stopped making new ones. That is the key. A dead galaxy is not a galaxy where everything has vanished. It is a galaxy where the factory has shut down. The machines are still there. The old workers are still there. The building still stands. But no new product is coming out. No new stars are being born. And that raises a big question. What killed it? Because galaxies are not supposed to die easily. Gravity pulls gas inward. Galaxies collide and merge. Fresh gas can fall in from the cosmic web. Stars die and return material back into space. The universe has many ways to feed galaxies. So when a massive galaxy stops forming stars, something serious has happened. Either the galaxy used up its cold gas too quickly, or something heated the gas so it could not collapse, or something blasted the gas out, or the galaxy was cut off from fresh fuel, or a supermassive black hole in the center became so powerful that it turned the galaxy's own heart against it. This is where dead galaxies become interesting, because they're not just dead objects. They are crime scenes. The stars are fingerprints. The gas is the missing weapon. The black hole is the suspect. And dark matter is the invisible structure holding the whole mystery together. When NASA's Hubble Space Telescope and ALMA studied 6 massive dead galaxies from the early universe, they found something strange. These galaxies existed when the universe was only around 3 billion years old. That period was supposed to be a wild age of star formation. Galaxies should have been building stars rapidly. The universe was younger, denser, and full of gas. But these 6 galaxies had already stopped. They were massive. They had formed stars before, but they were missing the cold hydrogen gas needed to keep forming more. They were, in simple terms, running on empty. That is terrifying for galaxy evolution models, because it means some galaxies were born, grew huge, and shut down very early. They lived fast. They burned hard. Then they died. And they left behind a question that still bothers astronomers. Where did the gas go? Because a galaxy cannot just decide to stop. Star formation needs fuel. If the fuel is gone, something removed it, heated it, or used it up. One possible answer is a starburst. A starburst is a period when a galaxy forms stars at an extreme rate. Instead of calmly producing a few stars each year, it may produce hundreds or even thousands. This can happen when galaxies merge. 2 galaxies collide. Their gas clouds crash. Gravity funnels gas toward the center. The pressure rises. Star formation explodes. For a short time, the galaxy becomes a cosmic furnace. But that furnace can burn through the gas too quickly. The same massive young stars that formed during the starburst also die quickly. They explode as supernovae. Those explosions inject energy into the galaxy. They push gas around. They can drive winds. They can make it harder for new stars to form. So one path to a dead galaxy is simple but brutal. It eats too fast. It grows too fast. Then it starves. But starbursts may not be enough. Many massive dead galaxies are too large, too old, and too completely shut down for simple gas exhaustion to explain everything. This brings us to the central monster, the supermassive black hole. Almost every large galaxy seems to have one at its center. Most of the time, a black hole is not actively swallowing everything around it like a movie monster. It is not a vacuum cleaner. If gas and stars orbit safely, they can keep orbiting. But when gas falls too close, the black hole becomes active. Material spirals into an accretion disk. The disk heats up. Radiation blasts outward. Jets can shoot from near the black hole at incredible speeds. This turns a galaxy's center into an active galactic nucleus, an AGN, and an AGN can change the fate of an entire galaxy. This is one of the most important ideas in modern astrophysics. Black holes do not only destroy things, they regulate galaxies. They can heat gas. They can push gas outward. They can stop hot gas from cooling. They can shut down the future birth of stars. This process is called feedback. The black hole feeds. Then it releases energy. That energy affects the galaxy around it. In some cases, it may trigger star formation by compressing gas. But in massive galaxies, the more famous role is negative feedback. The black hole injects enough energy into the gas that the gas cannot cool into star-forming clouds. Imagine a city where rain never reaches the ground. Clouds exist, water exists, but before it can collect into rivers and reservoirs, heat keeps it suspended. That is what can happen inside and around a dead galaxy. There may still be gas, but it may be too hot, too spread out, too disturbed, too prevented from collapsing. So the galaxy looks dead, not because all material is gone, but because the material is locked in the wrong state. It cannot become stars. And this is where dead galaxies become even stranger. Inside them, you may find plenty of gas, but not the right kind. Star formation needs cold, dense gas. Hot gas does not collapse easily. If it is heated by black hole jets, shock waves, supernova explosions, or motion through a galaxy cluster, it can remain trapped in a useless state for billions of years. The galaxy may be surrounded by a halo of hot gas. It may contain gas from old dying stars. But if that gas cannot cool, the galaxy remains dead. It has material, but no future. That is one of the darkest ideas in astronomy. A dead galaxy may not be empty. It may be full of fuel it cannot use. Like a starving person locked inside a room full of frozen food with no fire. But black holes are only one suspect. Another killer is environment. Galaxies do not always live alone. Many live in groups or clusters. A galaxy cluster can contain hundreds or thousands of galaxies. Between those galaxies is hot gas. This gas can be millions of degrees. It shines in X-rays. It is thin, but it fills enormous space. When a galaxy falls through a cluster, it can move at high speed through this hot medium. The pressure can strip gas from the galaxy. Astronomers call this ram pressure stripping. It is like wind tearing leaves from a tree, except the wind is hot plasma. The tree is a galaxy, and the leaves are the cold gas clouds needed to form stars. Some galaxies become jellyfish galaxies because gas trails behind them in long glowing streams. That gas can sometimes form stars outside the galaxy, in the stripped tail. But inside the galaxy itself, the fuel supply is being removed. Over time, the galaxy fades. Its young stars die. No new stars replace them. The blue light disappears. The galaxy reddens. And another dead system joins a cosmic graveyard. There is also starvation, not dramatic stripping, not a violent explosion, just slow suffocation. A galaxy needs fresh gas from outside to continue star formation for a long time. It can recycle gas from dying stars, but that is usually not enough forever. If a galaxy stops receiving fresh cold gas from the cosmic web, star formation gradually declines. This is called strangulation or starvation. It is less cinematic than black hole jets, but it may be common. A galaxy can die slowly, not from one explosion, not from one collision, but from being cut off. The supply lines close. The remaining fuel gets used. The star-forming regions fade. The galaxy becomes quiet. And after billions of years, all that remains is an old red population of stars. That is why a dead galaxy is not just a dead object. It is a record of how the universe controls growth. Some galaxies die from internal violence. Some die from their environment. Some die from starvation. Some may die because their black holes become too powerful. And some may die because they formed so quickly in the early universe that they shocked our understanding of what galaxies can do. The James Webb Space Telescope has made this problem more intense. Before Webb, astronomers already knew dead galaxies existed. Large elliptical galaxies in the nearby universe are often old, red, and quiet. That made sense. The universe is old now. There's been plenty of time for galaxies to merge, burn through gas, and shut down. But Webb looks deep into the past. Because light takes time to travel, looking farther into space means looking earlier in cosmic history. And Webb has found evidence of massive quiescent galaxies very early. Some of these systems appear to have formed huge numbers of stars in short bursts, then stopped forming stars when the universe was still young. That is not just interesting. It is a problem. Because standard galaxy formation models expect massive galaxies to build up gradually. Small structures form first. They merge. They grow. Gas cools. Stars form. Over time, big galaxies emerge. But if a massive galaxy already existed and had already stopped forming stars only about 1 or 2 billion years after the Big Bang, something happened fast, very fast. The galaxy had to gather gas, convert it into stars, build a massive stellar population, then shut down, all in a cosmic blink. That is why dead galaxies are not boring. They are some of the strongest evidence that the early universe may have been more efficient, more violent, and more surprising than scientists expected. Now we can finally open the graveyard. What is actually hiding inside a dead galaxy? The first thing hiding inside is old light. A dead galaxy is usually dominated by old stars. Many of these stars are smaller and cooler than the massive blue stars that dominate young star-forming regions. Blue stars are bright, but they die quickly. Some live only millions of years. Redder, lower-mass stars can live for billions or even trillions of years. So when star formation stops, the bright blue stars disappear first. They burn out. They explode. They leave behind remnants. The remaining galaxy becomes redder, not because every star is red, but because the young blue population is gone. The galaxy becomes a fossil of past star formation. Its light tells astronomers when its stars formed. By studying the spectrum of the galaxy, scientists can estimate the ages of the stars, the chemical elements inside them, and how quickly the galaxy formed. A spectrum is like a barcode of light. Different elements absorb and emit light at specific wavelengths. Hydrogen leaves patterns. Calcium leaves patterns. Iron leaves patterns. Magnesium leaves patterns. From these patterns, astronomers can read the story of the galaxy. They can tell whether the stars formed slowly over billions of years or quickly in a violent burst. And in some dead galaxies, the evidence points to extreme speed. A huge stellar mass formed rapidly. Then star formation collapsed. That means a galaxy is hiding a burned-out memory of a massive ancient starburst. It is not just dead. It is the ash left after a cosmic fire. The second thing hiding inside is stellar corpses. When stars die, they do not simply vanish. Their endings depend on their mass. A star like the Sun will eventually become a white dwarf. It will shed its outer layers. Its core will remain behind. A white dwarf is incredibly dense, roughly the mass of the Sun squeezed into something about the size of Earth. In a dead galaxy full of old stars, there should be enormous numbers of white dwarfs. They are faint. They cool slowly. They're the glowing bones of stars that died long ago. More massive stars end differently. They can explode as supernovae. Their cores may collapse into neutron stars. A neutron star is even more extreme. It is city-sized but heavier than the Sun. Matter, inside it is crushed to terrifying density. A spoonful of neutron star material would weigh more than a mountain on Earth. Some massive stars collapse into stellar mass black holes. These black holes may drift silently through the galaxy. Some may be in binary systems. Some may feed on companion stars. Some may remain almost invisible. So inside a dead galaxy, there is not just old starlight. There is an underworld, white dwarfs, neutron stars, stellar black holes, cold remnants, collapsed cores, the remains of stars that once burned brightly when the galaxy was young. The living stars are what we see. The dead stars are what the galaxy hides. And because dead galaxies are old, that hidden population may be huge. A dead galaxy is like an ancient battlefield with explosions ended long ago, but the bodies remain. The third thing hiding inside is globular clusters. Globular clusters are dense, spherical collections of old stars. They can contain hundreds of thousands or even millions of stars packed into a relatively small region. They are some of the oldest objects in galaxies. In the Milky Way, globular clusters orbit in a halo, like ancient relics from a galaxy's early formation. Dead elliptical galaxies can have rich systems of globular clusters. Some giant galaxies have thousands. These clusters are important because they preserve information from early cosmic history. They're like time capsules. Their stars formed long ago. Their chemical compositions can reveal what kind of gas existed when they were born. Their orbits can reveal whether the galaxy grew through mergers. If a dead galaxy swallowed smaller galaxies in the past, their globular clusters may have survived and joined a larger system. So when astronomers study globular clusters around dead galaxies, they are not just counting old star balls. They are reconstructing the galaxy's past. Each cluster may be a surviving witness. Some may have formed inside the main galaxy. Others may have been stolen from smaller galaxies. A dead galaxy may look smooth and simple in a telescope image, but its globular clusters can reveal a violent history of cannibalism. The galaxy may have eaten others, and the clusters are the bones it could not digest. The fourth thing hiding inside is dust. This may sound surprising. If dead galaxies are old and quiet, why would they have dust? But many do. Dust can come from dying stars. It can survive from past gas-rich events. It can be brought in by mergers with smaller galaxies. It can exist in lanes, shells, or patches. Dust matters because it hides light. A galaxy may look dead in visible light, but infrared telescopes can reveal warmer dust and hidden activity. This is one reason the James Webb Space Telescope is so powerful. Webb observes mainly in infrared. Infrared light can pass through dust better than visible light. It can also detect the glow of older, cooler objects and very distant galaxies whose light has been stretched by cosmic expansion. That means Webb can look into places where Hubble could not see as clearly. And sometimes what looked like a calm galaxy becomes more complicated. Dust can hide star formation. Dust can hide feeding black holes. Dust can make a galaxy appear older, redder, or quieter than it really is. This is a major challenge. When astronomers call a distant galaxy dead, they need to be careful. Is it truly not forming stars? Or is star formation hidden behind dust? Is the red color from old stars? Or from dust blocking blue light? This is why spectroscopy matters. Images can fool us. Colors can fool us. But spectra reveal deeper evidence. They show whether young stars are present. They show emission lines from gas. They show absorption features from older stellar populations. They help separate a truly dead galaxy from a dusty living one. And this is why recent JWST confirmations are so important. They are not just based on pretty pictures. They use spectra to test whether these early galaxies really stopped forming stars. Because in astronomy, a dead galaxy is not declared dead by appearance alone. It needs evidence. The fifth thing hiding inside is hot gas. This is one of the most important hidden ingredients. A dead galaxy may lack cold gas, but that does not mean it lacks gas completely. Massive elliptical galaxies and galaxies in clusters often contain hot X-ray emitting gas. This gas can be millions of degrees. It is too hot and diffuse to collapse easily into stars. It can sit in and around galaxies like a heated atmosphere. The strange part is that this hot gas should sometimes cool. If gas cools enough, it should sink inward, become denser, and form stars. But in many massive systems, that does not happen at the rate expected. Something is keeping the gas hot. This brings us back to black hole feedback. Jets from a central supermassive black hole can inflate bubbles in hot gas. They can send shock waves through the surrounding medium. They can stir the gas. They can prevent it from cooling too fast. This is a cosmic thermostat. If gas cools and falls toward the black hole feeds. When it feeds, it releases energy. That energy heats the gas and slows future cooling. The system regulates itself. Not perfectly, not always, but enough to keep many massive galaxies dead for billions of years. This is one of the most powerful ideas in the universe. A black hole smaller than a galaxy by an enormous factor can still control whether the galaxy forms stars. The center controls the future. The sixth thing hiding inside is dark matter. This is the biggest hidden thing of all. Dark matter does not shine. It does not absorb light. It does not emit light. We cannot see it directly, but we see its gravity. Galaxies rotate in ways that cannot be explained by visible matter alone. Galaxy clusters hold together more strongly than visible mass allows. Light bends around massive structures because of gravity, and that bending reveals more mass than we can see. Dark matter is the invisible skeleton of galaxies. It shapes where galaxies form. It helps pull ordinary matter into structures. It surrounds galaxies in halos that extend far beyond the visible stars. A dead galaxy may stop forming stars, but its dark matter halo remains. That halo can be enormous. The visible galaxy may be only the bright central part of a much larger invisible structure. This matters because the death of a galaxy does not destroy its gravity. A dead galaxy still lives inside a dark matter halo. It can still attract smaller galaxies. It can still merge. It can still bend light. It can still sit at the center of a larger gravitational system. In some cases, the visible galaxy may look faint or dead, but the dark matter halo may dominate the mass. The dark matter is not dead. It was never alive, but it is the hidden architecture that allows the dead galaxy to remain a galaxy. Without dark matter, many galaxies would not behave the way they do. So when we ask what is hiding inside dead galaxies, the most honest answer is this. Most of the mass may be hiding, not as stars, not as gas, not as dust, but as invisible dark matter. The seventh thing hiding inside is a supermassive black hole. This is the most dramatic object in the dead galaxy. In many massive dead galaxies, especially giant ellipticals, the central black hole can be enormous. Millions, billions, sometimes tens of billions of solar masses. These black holes may not always be active. A sleeping black hole is difficult to detect unless we can measure the motion of stars or gas around it. But sleeping does not mean gone. It is still there, waiting. If gas falls in, it can wake up. If a star passes too close, It can be torn apart in a tidal disruption event. If another galaxy merges, fresh material can feed the center. The dead galaxy can suddenly flare. For a short time, the old quiet system can produce enormous energy. This is one of the reasons dead galaxies are not truly peaceful. They can hide dormant engines. A galaxy can look red and quiet for millions of years. Then a star wanders too close to the black hole. The star stretches. It tears. Half the material may escape. The rest falls inward. The black hole lights up. Telescopes detect a flare. For a moment, the dead galaxy screams. Then it fades again. That is what makes these systems so unsettling. Their violence is not always constant. It is episodic, hidden, waiting for the right trigger. A dead galaxy is not a corpse lying still. It is a locked room with something breathing inside. And the more Webb studies the early universe, the more disturbing the black hole story becomes. Astronomers are finding supermassive black holes very early in cosmic history. Some are so massive, so soon after the Big Bang, that scientists are still debating how they grew so quickly. Did they form from the collapse of massive first stars? Did they form from direct collapse of huge gas clouds? Did dense star clusters collapse? Did black holes grow faster than expected? Did they help build galaxies instead of simply growing inside them? This matters for dead galaxies because black holes may be part of the death mechanism. If early black holes grew quickly, they could have heated or expelled gas early. They could have shut down star formation sooner than expected. They could help explain why some galaxies became quiescent while the universe was still young. But this is not settled. That is why the topic is powerful. Dead galaxies are not just objects we understand. They are laboratories for unsolved problems. How fast can galaxies form? How fast can black holes grow? How does feedback really work? Why do some galaxies keep forming stars while others die? Why did some galaxies stop so early? And can a dead galaxy ever come back? This last question is more complicated than it sounds, because galaxies are not biological creatures. Death is not always final. A quiescent galaxy can sometimes be rejuvenated. If it receives fresh cold gas through a merger or interaction, star formation may restart. A smaller gas-rich galaxy can fall in. A stream of cold gas can be captured. A collision can disturb the system. Under the right conditions, the old galaxy can form new stars again. But for massive dead galaxies, especially those with strong black hole feedback and hot gas halos, revival may be difficult. The same processes that killed star formation may prevent it from returning. Fresh gas may be heated. It may be expelled. It may not settle properly. The black hole may wake up again and stop the comeback. So a dead galaxy may be dead in practice, even if not in absolute terms. It can contain gas. It can have stars. It can merge. It can flare. But its long-term ability to build new generations of stars may be broken. That is the real meaning of galactic death. Not the end of motion. Not the end of gravity. Not the end of light. The end of renewal. The galaxy still exists, but its future has been cut off. And that is why dead galaxies feel so strange. They are full of the past, but poor in the future. Now imagine flying into one. From millions of light years away, it might appear as a smooth reddish glow. No spiral arms like the Milky Way. No bright blue star-forming knots. No glowing nebulae scattered across disk arms. Just a huge elliptical haze, like a cosmic ember. As you approach, the smoothness begins to break. You would see stars everywhere, but many would be old, red giants, low-mass red stars, ancient stellar populations. You would pass globular clusters, dense balls of stars orbiting in the halo, like survivors from the first chapters of the galaxy's life. You might detect faint streams of stars, stretched across space. These streams are evidence of past mergers. A smaller galaxy came too close. Gravity tore it apart. Its stars became a ribbon. Over billions of years, the ribbon may fade into the larger galaxy, but with sensitive instruments, astronomers can still detect the ghost. This is another thing hiding inside dead galaxies. The remains of galaxies they destroyed. A giant dead elliptical may not have formed peacefully. It may be the product of many mergers. Each merger added stars. Some added gas. Some fed the black hole. Some triggered starbursts. Some helped transform disks into spheroids. The final galaxy looks calm because time has smoothed the evidence. But deep imaging can reveal shells, streams, ripples, and faint structures. The dead galaxy is not smooth because it was born smooth. It is smooth because the violence happened long ago, like a battlefield covered by dust. If you keep moving inward, the density of stars rises. Near the center, the gravitational field becomes stronger. The central black hole dominates the motions of nearby stars. You may not see it directly. Black holes are black because light cannot escape from inside the event horizon, but the region around it can reveal its presence. Stars may orbit at high speeds. Gas may form a disk. If material falls in, it heats and glows. Jets may blast outward. The galaxy may be dead in star formation, but its center may still hold one of the most powerful engines in nature. And around that center, there may be a dense population of old stars and stellar remnants. White dwarfs cooling in darkness. Neutron stars spinning. Black holes orbiting unseen. Binary systems exchanging mass. Occasional flares when objects interact. This is not empty. It is an ancient machine. Slow, dark, mostly quiet, but not dead in the simple sense. The next hidden layer is chemical memory. Every star carries chemistry. The first stars formed mostly from hydrogen and helium. Heavier elements were forged later in stars and supernovae. Carbon, oxygen, silicon, iron, nickel, calcium. The elements that make planets and life possible were built through stellar evolution. When a galaxy forms stars rapidly, its chemical enrichment also happens rapidly. Massive stars explode and spread heavy elements. Later generations of stars form from enriched gas. So the chemical composition of stars inside a dead galaxy can reveal how quickly it formed. If the stars are enhanced in certain elements, astronomers can infer a short, intense star formation history. The chemistry becomes a clock, not a clock with hands, a clock written into atoms. A dead galaxy hides its atomic archive. Its stars are not just lights. They are records. Each one formed from gas with particular history. Together, they tell us when the galaxy built itself, how long star formation lasted, and what kind of explosion shaped its material. This is why dead galaxies are useful. Living galaxies are messy. New stars form. Gas flows. Dust hides regions. Supernovae disturb the structure. Dead galaxies are quieter. Their star formation has stopped, so their stellar population is like a completed document. Astronomers can read it, and sometimes the document says something shocking. It says this galaxy formed most of its stars very early. It says it formed them quickly. It says the galaxy shut down before theory expected. That is not just a story about one galaxy. It is a challenge to our timeline of the universe. The universe itself is about 13.8 billion years old. For a long time, the simple picture was that galaxies build up gradually. Early galaxies should be small, chaotic, and actively forming stars. Big dead galaxies should appear later. But observations keep complicating this picture. Massive galaxies appear early. Black holes appear early. Quiescent galaxies appear early. The young universe was not simple. It was not weak. It was already building monsters. And some of those monsters were dying young. That phrase sounds strange. A young dead galaxy. But that is exactly what astronomers are finding. A galaxy can be ancient from our point of view because its light traveled billions of years to reach us. But at the time we see it, the universe itself was young. So if that galaxy had already stopped forming stars, then its life cycle was extremely compressed. Birth, growth, starburst, shutdown, all before the universe reached even a fraction of its current age. That is like finding the ruins of an old city in a place where civilization was supposed to have just begun. And inside those ruins, we find clues. Old stars, missing gas, dense cores, black holes, chemical fingerprints, dark matter halos. The mystery is not only what is hiding inside dead galaxies. The mystery is how they became dead so early. One possibility is that early galaxies were extremely efficient at turning gas into stars. If gas collapsed rapidly into dense central regions, star formation could explode. Within a few 100 million years, a galaxy could build a huge stellar mass. But that efficiency creates a problem. If too much gas becomes stars too quickly, feedback becomes intense. Massive stars produce radiation. They drive winds. They explode. The central black hole may feed. The combined energy may heat or expel the remaining gas. The galaxy builds itself and kills itself in the same process. Growth becomes death. Success becomes failure. The galaxy becomes too good at forming stars. And because it is too good, it runs out of future. Another possibility is that black holes formed early and grew fast. If central black holes became massive quickly, their feedback could shut down star formation early. This connects dead galaxies to one of the biggest puzzles in Webb astronomy. Why do we see massive black holes so early? Some early quasars contain black holes with masses of hundreds of millions or billions of suns. To grow that large so soon, black holes need favorable conditions. They may start from massive seeds. They may feed continuously. They may experience super-Eddington growth. Or our models may be missing something. If early black holes were common and powerful, they could have shaped early galaxies more strongly than expected. They may not have simply grown inside galaxies. They may have helped decide which galaxies lived and which died. That is a major shift. For years, we imagined galaxies as the main structures and black holes as objects inside them. But the early universe may have been more like a partnership. Gas built stars. Gas fed black holes. Stars change gas. Black holes change gas. Everything affected everything. And in some galaxies, the black hole may have won. It heated the fuel. It stopped the collapse. It turned a living system into a dead one. But even this is not the full answer, because dead galaxies are not all the same. Some are giant ellipticals. Some are compact quiescent galaxies in the early universe. Some are satellite galaxies that lost gas. Some are clustered galaxies stripped by environment. Some may be relic galaxies, almost unchanged since the early universe. A relic galaxy is especially fascinating. It is a galaxy that formed early and then avoided major growth or disruption. Most galaxies evolve through mergers. They change size. They gain stars. They accrete material. But a relic galaxy is like a preserved fossil. It may show us what massive galaxies looked like billions of years ago. NASA has discussed NGC 1277 as an example of a nearby relic candidate. This galaxy is unusual because it appears to contain old stars and may have avoided the normal growth history of other massive galaxies. Objects like this are precious. They let astronomers study early universe conditions without looking across almost the entire observable universe. A relic dead galaxy nearby is like finding a dinosaur frozen in ice. It gives detail that distant red dots cannot. And what do these relics hide? They hide the early universe in plain sight. Their stars formed long ago. Their structures may preserve ancient conditions. Their black holes may be unusually massive compared with their galaxies. Their globular clusters may reveal how they formed. They are not just dead galaxies. They are time machines. Now when people imagine dead galaxies, they often imagine elliptical galaxies. Ellipticals are smooth, rounded systems. They can be small or gigantic. They have little cold gas compared with spirals. They are often dominated by older stars. They are common in galaxy clusters. But not every elliptical is completely dead, and not every dead galaxy is a classic elliptical. Galaxy classification is more complicated. A galaxy can look disk-like but be quiescent. A galaxy can be red but dusty and still forming stars. A galaxy can be blue but low in star formation due to recent changes. So astronomers do not rely only on shape. They measure star formation rates. They measure spectra. They measure gas. They study infrared emission. They look for emission lines. They model stellar populations. They combine data from multiple telescopes. Because the universe likes to hide the truth, a galaxy can wear a mask. Dust can make a young galaxy look old. A weak AGN can hide inside a comm system. Old stars can dominate light, even if small amounts of star formation remain. Distant galaxies are especially hard. Their light is faint. Their images are small. Their colors are shifted by cosmic expansion. This is why Webb changed everything. Its infrared sensitivity helps astronomers study the early universe with far more detail. It can detect faint old stellar populations at high redshift. It can take spectra of distant galaxies. It can reveal whether galaxies that look dead are truly quiescent. And the more it sees, the more the timeline becomes uncomfortable. Some galaxies appear to have shut down too early. Some black holes appear too large too soon. Some structures appear too mature. This does not mean the Big Bang model is wrong. It means galaxy formation is more complex than our simpler models allowed. The universe is not breaking. Our assumptions are. Dead galaxies are one of the tools breaking them. Now let's go deeper into the first hidden population, the old stars. Old stars are quiet, but they are not useless. They are the main light source of many dead galaxies. Their distribution tells us about the galaxy's structure. In giant ellipticals, stars move in more random orbits than in spiral disks. The Milky Way has stars orbiting in a disk, giving a flattened spiral shape. Ellipticals are more like swarms. Stars move in many directions. This random motion can be the result of mergers. When galaxies collide, orderly disks can be disrupted. Gas can be consumed or expelled. Stars from both galaxies mix. The final object becomes smoother and rounder. So the motion of old stars can reveal the violence that created the dead galaxy. Astronomers measure velocity dispersion. This means how fast stars are moving in different directions. A high velocity dispersion suggests a massive, dynamically hot system. It also correlates with central black hole mass and galaxy quenching. In simple terms, the deeper and more powerful the central gravitational system, the easier it may be for feedback to keep the galaxy dead. This is not just about one black hole blasting once. It is about long-term balance. A massive galaxy has deep gravity. Gas from old stars gets returned into galaxy. That gas could cool, but supernovae and black hole feedback can keep it hot or push it out. The dead state must be maintained. A galaxy does not die once and remain dead automatically. It has to stay dead. That is the hidden maintenance problem. Old stars keep shedding gas. Mergers can bring fresh material. Hot halos can cool. Something must prevent renewed star formation. So dead galaxies are not passive fossils. They are systems actively preventing revival. Their death is being maintained. That is a powerful line for the audience. A dead galaxy is not dead because nothing happens inside it. A dead galaxy is dead because everything that happens inside it fails to create new stars. That is the difference. Motion continues. Gravity continues. Black holes remain. Stars evolve. Gas circulates. But renewal fails. The galaxy cannot restart its own future. Now, consider the stellar remnants. White dwarfs may be everywhere in a dead galaxy. They are hard to see individually at large distances, but they matter. Over time, white dwarfs cool and fade. In binary systems, a white dwarf can steal material from a companion star. If it gains enough mass or undergoes the right kind of runaway nuclear reaction, it may explode as a Type Ia supernova. Type Ia supernovae are important because they can occur in old stellar populations. This means even a dead galaxy can still produce powerful explosions. A galaxy with no new stars can still occasionally light up with a supernova. That is because the explosion does not always require a young massive star. It can come from old stellar remnants in binary systems. So the dead galaxy is not free from fireworks. It has delayed explosions. The past comes back. A star that died into a white dwarf long ago may later become part of a catastrophic event. This is another way dead galaxies hide activity. They do not have the constant bright chaos of star-forming galaxies, but they have rare, sharp events. A Type Ia supernova can briefly outshine billions of stars. For a short time, the dead galaxy gets a new bright point of light. Then it fades back into silence. Neutron stars can also hide in dead galaxies. Some may be pulsars, spinning and beaming radiation. Some may be magnetars, with intense magnetic fields. Some may merge with other neutron stars or black holes. Those mergers can produce gravitational waves. They can produce heavy elements through the R process, including gold and platinum. Even an old galaxy can host compact eject mergers. So when we look at a dead galaxy, we should not think of it as simple red light. It is a museum of extreme physics, dense matter, collapsed stars, relativistic gravity, nuclear ashes, hidden binaries, rare explosions, and at the center, the largest collapsed object of all, a supermassive black hole. The supermassive black hole is the deepest secret because it connects a galaxy's past, present, and possible future. In an active galaxy, the black hole announces itself. It feeds. It glows. It launches jets. But in a dead galaxy, the black hole may be quiet. It may have very little gas to feed on. It may be starving just like the galaxy. This is almost poetic, but it is also scientific. The same lack of cold gas that stops star formation can also limit black hole feeding. The galaxy and black hole can both become quiet because the fuel is gone or inaccessible. But quiet black holes are difficult to study. Astronomers need indirect methods. They measure how stars orbit near the center. They measure gas dynamics. They look for X-rays or radio emission. They look for flares. They compare the black hole mass to the galaxy's bulge mass. Over time, they have found relationships between galaxies and their central black holes. This suggests coevolution. The galaxy affects the black hole. The black hole affects the galaxy. They grow together, fight together, and sometimes shut down together. Dead galaxies are where we see the aftermath. The black hole may be the ancient engine that helped end star formation, but it may now be quiet because there is little left to eat. A killer starving in the house it destroyed. That is a cinematic truth of some dead galaxies. But we have to be careful. Not every dead galaxy was killed by its black hole. Science is not one simple villain story. Some galaxies die mainly from environment, some from gas exhaustion, some from starvation, some from mergers, some from multiple processes at once. The universe rarely uses one weapon. It uses combinations. A merger can drive gas inward and trigger a starburst. That same gas can feed a black hole. The black hole can launch feedback. Supernovae can drive winds. A cluster environment can strip remaining gas. Fresh inflow can stop. Together, these processes can quench the galaxy. This is called quenching. Quenching means the shutting down of star formation. It is one of the biggest unsolved problems in galaxy evolution. We know galaxies quench. We see the result, but the exact path can differ, and the details are still debated. This is why the title works. What is hiding inside dead galaxies? Not one thing, many things. Old stars hide the timeline. Stellar remnants hide the afterlife of stars. Globular clusters hide the galaxy's childhood. Dust hides possible activity. Hot gas hides unusable fuel. Dark matter hides most of the mass. Black holes hide the central engine. Chemical patterns hide the speed of formation. Stellar streams hide cannibalism. And early quiescent galaxies hide a challenge to our models of the universe. Now, let's bring the viewer to one of the strongest images. A dead galaxy is like a city after an empire fell. The roads still exist. The buildings still stand. The archives are still buried underground. The old machines are rusting in warehouses. There may still be power in the central reactor, but no new children are being born. No new homes are being built. No future generation is replacing the old one. The city has not disappeared, but its story has changed from growth to memory. That is a dead galaxy. It shines with the past, but it no longer builds a future. And the most disturbing part is that our own Milky Way has a future in this story. The Milky Way is alive today. It still forms stars. It still has gas. It still has spiral arms. But it will not remain the same forever. In about several billion years, the Milky Way and Andromeda are expected to merge. This future collision will not be like two solid objects smashing. Stars are so far apart that most would not collide directly. But gravity will reshape both galaxies. Gas clouds may collide. Star formation may increase for a time. The central black holes may eventually interact. Over long timescales, the two galaxies may form a larger elliptical-like remnant. Star formation may eventually decline. The Milky Way as we know it may disappear. Not instantly, not violently from our human point of view, but cosmically, its identity will change. Our living spiral may become part of a quieter, older system, a future dead galaxy. That means dead galaxies are not only distant objects, they may be our future. When we study them, we study the possible end state of galaxies like our own. The question is not just what is hiding inside dead galaxies. The question is what will one day hide inside ours. The sun will be gone. Earth will not be the world we know. The Milky Way's spiral structure may be erased. And somewhere inside the future merged galaxy, old stars, white dwarfs, black holes, globular clusters, and dark matter will continue orbiting in a quiet gravitational sea. The future of a galaxy is not darkness. It is fading, slowly, over timescales too large for the human mind to hold. But long before that ultimate fading, dead galaxies are already telling us something urgent. The universe is not just a place where things form. It is a place where things stop forming. Growth is not guaranteed. Fuel runs out. Feedback turns against creation. Environments strip galaxies bare. Black holes regulate life and death on cosmic scales. The same universe that makes stars also builds the mechanisms that prevent them. This is the balance. Creation and quenching. Fire and starvation. Birth and silence. And inside the silence, the evidence remains. The stars do not lie. Their ages show when the galaxy formed. Their chemistry shows how fast it enriched. Their motion shows mergers and gravity. Their absence of youth shows the factory stopped. The gas does not lie either. If cold gas is missing, the galaxy cannot build new stars. If hot gas remains, the galaxy may have fuel locked in a useless state. If dust hides activity, infrared telescopes can expose it. If a black hole feeds, X-rays and radio jets may reveal the central engine. Every wavelength tells a different truth. Visible light shows stars. Infrared shows dust and old populations. Radio can show cold gas and jets. X-rays show hot gas and energetic black hole activity. No single telescope sees the whole dead galaxy. That is why astronomers combine them. Hubble gives sharp visible and ultraviolet views. ALMA traces cold dust and gas. Chandra sees X-rays from hot gas and energetic objects. Webb sees infrared light from dust, old stars, and the early universe. Together, they turn a dead galaxy from a red blur into a layered system, and each layer hides a different part of the story. If the galaxy is missing cold hydrogen, ALMA helps reveal that. If old stars dominate, Hubble and Webb help map them. If hot gas fills the system, Chandra can detect X-rays. If dust hides the center, infrared observations can pierce through. If dark matter bends light, gravitational lensing can expose invisible mass. This is a modern way we study cosmic death, not by looking once, but by interrogating the galaxy across the spectrum. The dead galaxy becomes a suspect under different lights, and under each light, another secret appears. One of the biggest secrets is size. Early dead galaxies found at high redshift are often compact. Some are much smaller than massive elliptical galaxies today, even if they contain huge stellar mass. This means they are dense, very dense, a massive number of stars packed into a relatively small region. Over time, many of these compact dead galaxies may grow in size through mergers, not necessarily by forming many new stars, but by adding stars from smaller galaxies around their outskirts. This is called dry merging. A dry merger is a merger with little gas. It adds stars without triggering much new star formation. So a dead galaxy can keep growing while staying dead. That sounds contradictory, but it is real. Growth does not always mean new stars. A dead galaxy can grow by cannibalism. It can swallow smaller galaxies. It can build a larger outer envelope. It can become bigger and more massive. But if the merger is gas poor, it remains quiescent. It expands without renewing. This may explain how compact early dead galaxies became the giant ellipticals we see today. They formed dense cores early, then grew outward through mergers. So inside a modern dead elliptical, the central core may be ancient. The outer regions may have been added later. This means different parts of the same galaxy can have different histories. The center may be the original ancient dead galaxy. The outskirts may be the remains of smaller galaxies swallowed over billions of years. The galaxy is not one fossil. It is a fossil collection, a core from the early universe, a halo from later mergers, globular clusters from different origins, streams from recent accretion, dark matter from hierarchical growth, hot gas shaped by feedback. This is why dead galaxies are not simple. They look smooth because we are far away, but physically they are layered, like tree rings, except the rings are made of stars, chemistry, and gravity. Another hidden feature is the stellar halo. A stellar halo is a diffuse population of stars surrounding a galaxy. These stars are often old. Many may come from disrupted smaller galaxies. The halo is faint. It is hard to observe, but it can reveal a galaxy's merger history. In dead galaxies, the halo may contain evidence of past accretion events. Shells and tidal streams can appear when a smaller galaxy is torn apart. These features fade over time, but deep observations can still detect them. The smoother the galaxy, the older or more mixed its merger history may be. The more visible the streams and shells, the more recent the disruption may be. So dead galaxies hide there, violence and faint outskirts. The center tells one story. The halo tells another. A telescope looking only at the bright center misses the crime scene. The outskirts may reveal the bodies. The next hidden secret is metallicity. In astronomy, metals mean elements heavier than hydrogen and helium. That includes oxygen, carbon, iron, magnesium, and everything else heavier. A galaxy's metallicity tells us how enriched its stars are. High metallicity means many previous generations of stars had already lived and died, producing heavier elements. Some massive dead galaxies have stars with high metallicity. This suggests intense early star formation and rapid chemical enrichment. Another important clue is alpha enhancement. Alpha elements like oxygen, neon, magnesium, silicon, and sulfur are produced mainly by massive stars that explode quickly as core collapse supernovae. Iron is produced significantly by type Ia supernovae, which often occur on longer timescales. So if a galaxy's stars are alpha enhanced, it can suggest that star formation happened quickly. Massive stars enrich the gas fast. Then star formation stopped before type Ia supernovae could add as much iron. This is like reading the tempo of the galaxy's birth. High alpha enhancement can mean the galaxy built its stars in a short, violent burst. Again, the dead galaxy is not quiet evidence. It is loud, if you know how to read it. Its chemistry says, I form fast. Its colors say, I am old. Its gas says, I cannot build. Its black hole says, I may have stopped the future. Its dark matter says, I still hold everything together. Now, we should talk about the word dead itself. Astronomers use it because it is simple and dramatic, but scientifically, quiescent is better. Quiescent means quiet. It means star formation is very low or absent compared with star-forming galaxies. A quiescent galaxy is not dead in every physical sense. Stars still orbit. Stars still evolve. Black holes still exist. Gas may still move. Dark matter still shapes gravity. So the word dead is a shortcut, a useful one, but also dangerous, because it can make people imagine emptiness. And dead galaxies are not empty. They are some of the most crowded graveyards in the universe. They contain more history per unit of light than almost anything else. This is the core message of the video. Dead galaxies are not empty. They are full of evidence. The death is not the absence of objects. The death is the absence of new star birth. And once the audience understands that, the entire title becomes stronger. What is hiding inside dead galaxies? The answer is not aliens, not magic, not a literal monster. The real answer is better. A dead galaxy hides a universe's memory of growth, violence, starvation, and control. It hides a proof that even cosmic giants can run out of future. And it hides a warning. If a galaxy can build hundreds of billions of stars and still lose the ability to create more, then size does not guarantee life. Power does not guarantee renewal. Even the largest systems can become old, red, quiet, and trapped. Let's go back to the early universe. The first galaxies formed from small density fluctuations after the Big Bang. Dark matter clumped first, creating gravitational wells. Gas fell into those wells. As gas cooled, the first stars formed. These early stars may have been massive and short-lived. They produced the first heavy elements. Over time, galaxies grew through accretion and mergers. The cosmic web fed them. Filaments of gas connected structures across space. Galaxies were not isolated islands. They were nodes in a network. During cosmic noon, roughly around 10 to 11 billion years ago, star formation across the universe peaked. This was the great age of galaxy growth. Many galaxies were forming stars at high rates. But during or even before this period, some massive galaxies had already shut down. That is the shock. At the time when the universe was making stars most aggressively, some galaxies were already dead. This is like finding closed factories during an industrial boom. Everything around them is producing, but they are silent. Why? That question is why astronomers study them. If they die because they lost gas, we need to know how. If they die because black holes heated the gas, we need to know how strong the feedback was. If they die because they formed too quickly, we need to know how gas became stars so efficiently. If they die because the environment stripped them, we need to know when clusters became powerful enough to do that. Every answer changes our model of galaxy evolution, and sometimes the answer may be different for different galaxies. That is why there is no simple script that says black holes killed all dead galaxies. That would be easy, but it would be wrong. The better story is more interesting. Galactic death is not one event. It is a set of pathways. A galaxy can be quenched by internal feedback, by environmental stripping, by gas exhaustion, by starvation, by morphological stabilization, where the structure of the galaxy makes gas less likely to collapse, by mergers that heat stellar orbits and consume gas, by halo heating, where gas falling into massive halos becomes shock-heated and cannot cool efficiently. These processes can overlap. In a massive galaxy, the halo may heat gas. The black hole may prevent cooling. Mergers may disturb the system. Starbursts may consume fuel. The result is quenching, but the path is complex. This is important for making the video feel intelligent. Do not make the galaxy death too simple. Make it feel like a mystery with multiple suspects, because that is exactly what it is. And the strongest suspect, again and again, is the black hole, not always alone, but often central. Black hole feedback is powerful because it explains how a galaxy can remain dead even when gas exists. It explains the maintenance problem. It explains why massive galaxies, especially those with deep gravitational wells, can stop forming stars. It connects the smallest central region to the largest galactic outcome. A black hole's event horizon may be tiny compared with a galaxy, but the energy released by accretion can affect gas across thousands or even hundreds of thousands of light years. That is insane. A central object can influence the fate of billions of stars worth of material. This is the universe's version of a small switch controlling a giant machine. And in dead galaxies, the switch may be stuck in the off position. Not off for the black hole, off for star formation. But black holes are not always destructive. Sometimes their jets compress gas and trigger star formation. Sometimes feedback is positive. This makes the story even more interesting. The same black hole physics can create or prevent stars depending on conditions. It is not good or evil. It is a regulator. In one environment, it sparks birth. In another, it blocks it. In massive dead galaxies, the blocking role may dominate. The black hole keeps gas hot, turbulent, or expelled. The galaxy remains red and quiet, and the center holds a machine that may have locked the future. Now, let's imagine a dead galaxy in a cluster. The cluster is filled with hot gas visible in X-rays. The galaxy moves through it. Its own gas halo interacts with the cluster medium. If the galaxy is a smaller satellite, ram pressure may strip its gas. If it is a massive central galaxy, it may sit at the bottom of the cluster's gravitational well. Hot gas should cool and fall inward, but the central black hole sends jets into the gas. The jets carve cavities. They inflate bubbles. They generate sound waves and shocks. They distribute energy. They stop a cooling catastrophe. Without that heating, enormous amounts of gas might cool and form stars. With it, star formation is limited. The dead galaxy stays dead. This is not science fiction. X-ray observatories have seen cavities in hot gas around galaxies and clusters. Radio observations show jets filling those cavities. The black hole is not directly visible as a monster. Its fingerprints are visible in the gas. Bubbles, jets, shock fronts, temperature structures. The galaxy's silence is being maintained by invisible violence. That is a strong image. A dead galaxy looks quiet because the violence is happening in gas too hot and thin for human eyes. The next hidden secret is time. Dead galaxies are time machines because their stars preserve old light. When we observe a distant dead galaxy, we see it as it was billions of years ago. If it is already dead in that ancient light, then it died even earlier. That means its birth and death happen at redshifts beyond what we directly see. Astronomers reconstruct that history through stellar population models. They ask, when did the stars form? How long did star formation last? When did it stop? How much dust is present? What is the mass? What is the star formation rate? These answers are uncertain, especially for distant galaxies. But JWST spectroscopy improves them. Spectroscopy can detect absorption features that indicate older stars. It can show lack of emission lines that would indicate strong ongoing star formation. It can help confirm quiescence. This is why the discovery of early massive quiescent galaxies matters. It is not just another object. It is a measurement of time. It tells us the universe was capable of making and shutting down massive systems earlier than expected. A dead galaxy is not only a place. It is a date that may be too early for comfort. And if future Webb surveys find more of them, the problem grows. One rare object can be an outlier. Many objects become a pattern. If early dead galaxies are common, simulations must explain them. They must produce rapid star formation, rapid quenching, massive black holes, dense stellar cores, correct number densities, correct chemical histories. That is hard. Modern cosmological simulations are powerful, but they depend on models of physics too small to resolve directly. Star formation, supernova feedback, black hole accretion, AGN feedback, gas cooling, dust, radiation. These processes are complex. If simulations underproduce early quiescent galaxies, it may mean the feedback recipes are incomplete, or star formation efficiency is underestimated, or black hole growth is different, or observational interpretation needs refinement. This is how science moves, not by pretending everything fits, but by finding the places where it does not. Dead galaxies are one of those places. They are quiet objects causing loud problems. Now, let's talk about the most invisible possibility: failed galaxies and dark halos. Not every dark matter halo forms a bright galaxy. Some halos may contain little or no star formation. Gas may be prevented from cooling. Ultraviolet radiation from the early universe may keep gas ionized. Supernovae or environmental effects may remove baryons. There may be dark or nearly dark systems dominated by dark matter. These are not the same as classic dead galaxies, because a dead galaxy usually formed stars and then stopped. A failed galaxy may barely form stars at all, but they are connected by one idea. The universe may contain many structures that are mostly invisible. Some are dead because their stars are old. Some are dark because stars never formed efficiently. Some are faint because dark matter dominates and ordinary matter is scarce. This expands the title. What is hiding inside dead galaxies? Maybe not only the dead galaxy itself. Maybe the space around it hides dark satellites, stripped halos, and faint relics of smaller systems it consumed. A giant dead galaxy may be surrounded by small satellite galaxies. Some may be ultra-faint. Some may be mostly dark matter. Some may eventually fall in and be torn apart. The dead galaxy continues to grow by eating its surroundings. Even in death, it participates in cosmic evolution. This is a paradox. Dead galaxies are not forming stars, but they are still evolving. They can merge. They can accrete satellites. They can grow in size. Their black holes can flare. Their hot gas can be stirred. Their stars can age. Their remnants can collide. Their dark matter halos can merge. So dead only describes one process, star formation. It does not describe the entire system. This is why the script should avoid saying dead galaxies do nothing. They do many things. They just do not make many new stars. And that one failure changes everything. Because stars are how galaxies renew their light. Without new stars, the galaxy fades and reddens. Its massive stars die first. Its gas disappears or becomes useless. Its future becomes quiet. Over huge timescales, even the remaining stars will evolve. More will become white dwarfs. Some will become neutron stars or black holes. The galaxy will become increasingly dominated by remnants and low-mass stars. Far in the future, star formation across the universe will decline. The cosmic star factory will slow. Dead galaxies are not just objects in the universe. They are previews of the universe's far future. A future where star formation becomes rare, where galaxies fade, where the bright age of stars slowly gives way to darkness. That is why the topic has emotional power. Dead galaxies show us that the universe has an aging process. It had a childhood. It had a wild youth. It had a star-forming peak. And it has a future where creation becomes harder. The universe is not static. It is using up accessible fuel. It is expanding. Structures evolve. Stars die. New stars form less easily over time. Dead galaxies are local examples of a larger cosmic trend. They are places where the future arrived early. Now let's shape the story around a viewer's curiosity. The viewer clicks because of the title. What is hiding inside dead galaxies? They expect mystery. We give them mystery, but based on science. We start by breaking the assumption. A dead galaxy is not empty. Then we explain what dead means. Not no stars. No new stars. Then we introduce the hidden contents one by one. Old stars. Stellar corpses. Globular clusters. Dust. Hot gas. Dark matter. Black holes. Chemical clues. Faint stellar streams. Then we escalate. Some dead galaxies are ancient. Some died early. Some may challenge models. Some may contain black holes that help kill them. Some may be our own galaxy's future. Then we end with a big idea. The dead galaxy is not a grave with nothing inside. It is a locked archive of the universe. The universe hides its past inside dead galaxies. And every time Webb looks deeper, the archive becomes stranger. That is the direction. Now we can continue the script deeper, moving from the contents into individual mysteries. The first mystery is the missing gas. Because no matter how beautiful the old stars are, a galaxy dies when the cold gas disappears or stops working. Cold hydrogen is the basic fuel for star formation. Astronomers can trace gas in different ways. Neutral hydrogen can be observed in radio wavelengths. Molecular gas is often traced through carbon monoxide emission. Cold dust can act as a proxy for cold gas in distant systems. ALMA is extremely important here because it can observe millimeter and submillimeter wavelengths from cold dust and gas. When ALMA fails to find enough cold gas in a massive quiescent galaxy, that tells us the star-forming reservoir is missing or severely depleted. This is what makes early dead galaxies so mysterious. They are not just red. They are fuel-poor, at least in the observations we have. If a galaxy lacks cold gas, there are several possible explanations. It may have converted the gas into stars. It may have expelled gas through winds. It may have heated gas beyond the cold phase. It may have been prevented from receiving fresh inflow. It may have had gas stripped away by environment. The missing gas is the central clue. Everything else is secondary, because without cold gas, the galaxy cannot build new stars. So the question becomes, who took the gas? A starburst can take it by consuming it. Supernovae can push it. A black hole can heat it or expel it. A cluster can strip it. The cosmic web can stop supplying it. Sometimes, the answer may be all of them. Imagine a young massive galaxy in the early universe. Gas pours in. The galaxy forms stars violently. The central black hole feeds. Supernovae explode. The black hole launches winds. Gas is heated and expelled. The galaxy suddenly loses its cold reservoir. For a short time, it was one of the brightest star-forming systems in its region. Then the fuel is gone. The massive blue stars die. The galaxy turns red. By the time Webb observes it, the fire is already ended. Only the ashes remain. This is a live fast, die young galaxy. And it may be one of the most important objects in cosmology, because it tells us that early galaxies could evolve faster than expected. The second mystery is the black hole. In a living galaxy, gas can flow toward the center and feed the black hole. But in a dead galaxy, the black hole may be dormant. How do we know it is there? In nearby galaxies, astronomers can measure star motions near the center. Stars orbit faster when there is more mass inside their orbit. If the central mass is extremely compact, the best explanation is a black hole. In more distant galaxies, it is harder. Astronomers may infer black hole activity from X-ray emission, radio jets, infrared signatures, broad emission lines, or other AGN indicators. But many black holes are hidden. Dust can obscure them. Low accretion rates can make them faint. A dead galaxy may hide a black hole that shaped its history, but now leaves only faint evidence. This is like finding a burned city with the furnace cold. The furnace may have caused a fire, but now it is not burning. The evidence is indirect. Gas missing. Stars old. Center massive. Hot halo disturbed. Jets fossilized. Cavities in X-ray gas. Radio lobes fading. The black hole's past violence may be written into the surrounding medium. Astronomers sometimes find radio relics or X-ray cavities from previous AGN outbursts. These are fossil signatures of black hole activity. The black hole does not need to be active now. Its older outbursts may have left scars. This is another thing hiding inside dead galaxies. Not just objects. Scars. A galaxy can remember violence in its gas, stars, and structure. The third mystery is the core. Massive dead galaxies often have dense central regions. Some may have cores shaped by black hole binaries. When galaxies merge, their central black holes may sink toward the center of the new galaxy. Over time, the black holes form a binary. As they orbit, they can interact with nearby stars and fling them outward. This can carve out a low-density core in the central stellar distribution. Eventually, the black holes may merge, producing gravitational waves. This process is difficult and slow, but it is important for understanding giant ellipticals. So the center of a dead galaxy may hide evidence of past black hole mergers. A smooth galaxy may have had multiple central monsters. They may have spiraled together. They may have ejected stars. They may have merged into one larger black hole. Again, dead does not mean simple. It means the star factory stopped. The gravitational drama continued. The fourth mystery is the outskirts. The outskirts of dead galaxies are faint, but they can reveal growth through mergers. A galaxy may have a compact ancient core and a large outer envelope built later. Minor mergers add stars to the outskirts more efficiently than the center. Over billions of years, repeated minor mergers can puff up a compact galaxy into a giant elliptical. This helps explain why massive quiescent galaxies in the early universe can be much smaller than similar mass galaxies today. They may be the dense seeds. Later dry mergers build the outer body. If this is correct, then modern dead galaxies hide ancient compact dead galaxies inside them. Their cores are older than their outskirts. Their centers form fast. Their halos grew slowly. This is a beautiful idea. A dead galaxy is like a fossil inside a fossil. The center is the original relic. The outer regions are later additions. And the whole object is held inside a dark matter halo that grew through cosmic mergers. The fifth mystery is whether dead galaxies can restart. Some can. If a quiescent galaxy accretes cold gas, it may form stars again. If it merges with a gas-rich galaxy, star formation can be rejuvenated. Some galaxies show signs of recent small star-forming episodes after long quiet periods. But massive dead galaxies often resist revival. Why? Because gas does not only need to arrive. It needs to cool. It needs to settle. It needs to become dense. It needs to avoid being heated or expelled. If the galaxy has a hot halo and strong black hole feedback, new gas may not survive as star-forming fuel. The death mechanisms remain active, so revival is possible but not guaranteed. A dead galaxy may receive fuel and still fail. This is one of the most tragic ideas in the script. The galaxy may be offered another chance, but its own structure refuses it. A deep gravitational halo heats infalling gas. The central black hole prevents cooling. The stellar population is old. The gas cannot settle into a disk. The galaxy swallows material but does not create a new generation. It grows, but does not live. Now, bring this back to the audience. When you look at an image of a dead galaxy, you may see a smooth red oval. It may look boring next to a spiral galaxy full of blue arms and glowing nebulae, but the boring one may be hiding the bigger story. A spiral galaxy shows active creation. A dead elliptical shows a result of cosmic evolution. It tells us what happens after creation peaks. It tells us what remains after the starburst ends. It tells us how black holes, dark matter, gas, and gravity control the long-term fate of galaxies. It is not visually loud. It is scientifically loud. The universe hides some of its biggest secrets in the quietest objects. That line should sit near the middle or end of the full script, because it captures the theme. The loudest galaxies are not always the most important. A quasar screams. A starburst shines. A supernova explodes. But a dead galaxy whispers across billions of years. And inside that whisper is a timeline of cosmic death. The next part of the script should go deeper into the early universe and Webb, because this is where the video becomes modern and fresh. Webb did not just give us prettier images. It gave us deeper evidence. It sees infrared light from galaxies whose visible and ultraviolet light has been stretched by the expansion of the universe. This redshift moves ancient light into infrared wavelengths. So Webb is built for cosmic archaeology. When it finds a quiescent galaxy at high redshift, it is not simply seeing an old galaxy. It is seeing a galaxy that was already old when the universe was young. This is what makes early dead galaxies so shocking. They force us to compress the timeline. The stars inside them must have formed even earlier. If a galaxy is observed 1.2 billion years after the Big Bang and already has a large old stellar population, then the stars may have formed hundreds of millions of years before that. That pushes major galaxy formation into an extremely early period. It asks a brutal question. How did the universe build something so mature so fast? One answer is that dense regions of the early universe evolved rapidly. Not all parts of the universe grow at the same pace. Some regions are overdense. They contain more matter. They collapse earlier. They form galaxies earlier. In those special regions, massive structures may arise quickly, but even then, massive quiescent galaxies are difficult. They require not just early formation, but early shutdown. Formation alone is not enough. The galaxy had to build and stop. That is the double challenge. It is like finding not just a skyscraper built early, but an abandoned skyscraper already covered in dust. The building was completed, used, then shut down, all before the city around it fully developed. This is why scientists care. Dead galaxies are not just old. They are early completed systems. They may represent the first wave of massive galaxy evolution, and they may be the ancestors of today's giant ellipticals. When we look at a giant elliptical nearby, we may be seeing the final expanded version of those compact early dead systems. The core may have formed in a violent burst. The black hole may have grown early. The galaxy may have quenched. Then for billions of years, it grew through dry mergers. It added stars. It added dark matter. It added globular clusters. But it did not restart major star formation. The galaxy became larger, but not younger. That is how a dead galaxy can evolve without truly living again. Now, what about planets? If a dead galaxy has old stars, could it have planets? Almost certainly, yes, in principle. Planets form around stars in many environments. The Milky Way has billions of planets. Old stars can have planets. But dead galaxies are hostile to new planet formation because new stars are not forming. Planets around old stars would also be old. Many may orbit red dwarfs or evolve stellar systems. Some may have survived stellar evolution. Some may have been destroyed when their stars became red giants. Some may orbit white dwarfs. But from a video perspective, be careful. Do not turn the script into alien speculation. Keep it science-based. You can say dead galaxies may contain old planetary systems, but we do not have a complete census of planets in distant dead galaxies. The main point is that dead galaxies are not empty of worlds. They could contain ancient planetary systems orbiting old stars. But the galaxy is not actively making many new stars, and therefore not creating many new planetary systems. That gives a powerful idea. Inside a dead galaxy, any planets will belong to an older cosmic generation, worlds around aging stars, planets under red light, systems born when the universe was younger. But because the galaxy is no longer forming stars, the age of new worlds has ended. Again, the theme is renewal. Old systems remain. New systems stop. Now we should introduce one of the most haunting possibilities. A dead galaxy may contain life-bearing planets from ancient times, but a galaxy itself no longer produces many new suns. This is speculative in terms of life, so phrase it carefully. Do not claim life exists there. Say if planets exist around long-lived stars, then some have been stable for billions of years, but whether life exists is unknown. This adds wonder without fake claims. But for the main scientific script, keep focus on stars, gas, black holes, and dark matter. Now let's return to dark matter. Dark matter is essential because dead galaxies show that visible light is not the full story. A dead galaxy may be faint compared with its mass. Its old stars emit less blue light. Its star formation is low, but gravitationally it remains powerful. Its dark matter halo can dominate its mass and extend far beyond the visible galaxy. In galaxy clusters, dark matter is even more important. Clusters are held together by gravity from galaxies, hot gas, and dark matter. Gravitational lensing reveals mass distributions, including invisible matter. When a dead galaxy acts as a gravitational lens, it can bend light from objects behind it. This can help astronomers measure its mass, including dark matter and central mass structure. So dead galaxies can be used as cosmic lenses. They hide mass, but they also reveal mass by bending light. This is one of the beautiful contradictions. Dark matter cannot be seen directly, but its gravity changes what we see. A dead galaxy may be visually quiet, but gravitationally loud. It can warp background light. It can magnify distant galaxies. It can help us see deeper into the universe. So even a dead galaxy can become a telescope. Its gravity becomes glass. That is a strong cinematic line. The galaxy is dead, but its gravity still helps us see the living universe behind it. Now we have enough material to build the second half of the full script. The next part should go into individual hidden objects and mechanisms with stronger escalation. Start with the old stars, then the stellar remnants, then the black hole, then the missing gas, then the dark matter halo, then the early universe mystery, then the future of the Milky Way, then the cosmic ending. The final ending should feel big, unresolved, and slightly haunting. Something like, dead galaxies are not empty graves. They are locked archives. And the deeper Webb looks, the more those archives tell us that the universe learned how to build, burn, and bury galaxies much earlier than we expected. But we are not finished, because the most important thing hiding inside dead galaxies may not be any object at all. It may be a warning. A galaxy can have billions of stars and still lose its future. And one day, the same silence may be waiting for us. But the most important thing hiding inside dead galaxies may not be a star, black hole, or a cloud of gas. It may be time, because every dead galaxy is a clock that stopped ticking. Not because motion stopped, not because gravity stopped, not because every star disappeared, but because the one process that keeps a galaxy young finally failed. Starburst stopped. That is why dead galaxies feel so unsettling. They are not ruined because they are empty. They are ruined because they are complete. Their greatest chapter already happened. Their brightest age is behind them. And everything left inside is a clue pointing backward. When astronomers study a dead galaxy, they are not only asking what is inside it today, they are asking what happened before the silence. How fast did it form? How much gas did it consume? Did it suffer a violent starburst? Did its black hole wake up and attack its own fuel supply? Did the galaxy fall into a cluster and have its gas stripped away? Did it stop receiving fresh material from the cosmic web? Or did all of these things happen together? That is why the dead galaxy is not just an object. It is a crime scene billions of light years wide. And the first thing every crime scene needs is a timeline. A living galaxy keeps writing new pages. New stars form. Young blue stars appear. Gas clouds collapse. Supernovae explode. New chemical elements spread into space. The galaxy keeps changing its own story. But a dead galaxy is different. When star formation stops, the main writing stops. After that, the stars mostly age. They grow redder. They evolve. They die. They leave remnants behind. So the galaxy becomes easier to read in one sense. Its stars become an old population, a record of an earlier event, a fossilized memory of when the galaxy was young, bright, and violent. This is why astronomers care so much about the light from dead galaxies. Light is not just brightness. Light is information. When a telescope captures light from a dead galaxy, it is catching ancient messages carried by photons across cosmic time. That light contains colors. Those colors reveal temperature. It contains absorption lines. Those lines reveal elements. It contains shapes in the spectrum. Those shapes reveal the ages of stars. And when scientists combine all of that, they can begin to reconstruct the galaxy's life. A dead galaxy may look like a smooth red glow, but hidden inside that glow is a history of hydrogen, helium, oxygen, iron, magnesium, carbon, supernovae, black holes, and gravity. It is not one color. It is a code, and the code says something very strange. Some galaxies built themselves fast, too fast. They formed huge numbers of stars in a short period. Then, before the universe was even middle-aged, they stopped. That is the part that makes dead galaxies dangerous to our models. Because the universe was not supposed to produce so many mature dead systems so early. In the simplest picture, young galaxies should be messy, active, blue, and full of gas. Old dead galaxies should become common later. But the James Webb Space Telescope has pushed deeper into the early universe, and the picture is no longer that simple. Webb is finding that some galaxies were already massive, already mature, and already quiet when the universe was still young. That means their stars formed even earlier. It means their growth happened quickly. It means their shutdown happened quickly, too. And that forces one brutal question. How does a galaxy live its entire life so early? Imagine finding an abandoned palace in a city that was supposed to be only a village. The walls are already built. The rooms are already decorated. The people who build it are already gone. That is what early dead galaxies feel like. They should not look so finished. But they do. And the deeper astronomers look, the more these cosmic ruins force us to rethink the speed of creation. The first hidden secret is that dead galaxies are often not dead because they failed. They may be dead because they succeeded too violently. A galaxy needs cold gas to make stars. Cold gas collapses under gravity. It gathers into clouds. The clouds become dense. Dense regions become stars. But if a galaxy forms stars too rapidly, it can burn through its cold gas reservoir. For a short period, it becomes extremely productive. It turns gas into stars at a furious rate. But that success comes at a cost. The most massive stars die quickly. They explode as supernovae. They release energy. They blow winds. They stir the gas. They heat the surrounding medium. And if enough of this happens at once, the galaxy can damage the very environment it needs to continue forming stars. The galaxy builds itself and wounds itself at the same time. This is one possible path to death. Not weakness, overheating, overproduction, a cosmic factory working so hard that it destroys its own fuel system. That is why some dead galaxies feel almost tragic. They did not die because nothing happened. They died because too much happened too fast. And if a central black hole joined that process, the damage could become even stronger. A feeding supermassive black hole can release enormous energy. It can produce radiation. It can drive winds. It can launch jets. It can heat gas far beyond the central region. A black hole may be physically tiny compared with host galaxy, but the energy released around it can influence an entire galaxy's future. This is the strange power of black hole feedback. The black hole does not need to swallow every star. It does not need to eat the tea, only needs to disturb the fuel. If cold gas is removed, heated, or prevented from cooling, star formation dies. A galaxy can have hundreds of billions of stars and still lose its future because its gas is trapped in the wrong state. That is the difference between a living galaxy and a dead one, not the number of stars it has. the ability to make new ones. Inside dead galaxies, the central black hole may now be quiet, but quiet does not mean innocent. A black hole can act like a volcano that erupted long ago. The eruption ends. The smoke clears. The surface cools. But the landscape is changed forever. In galaxies, the evidence may be hot gas, missing cold gas, radio jets, bubbles in X-ray emitting plasma, disturbed central regions, or chemical signs that star formation stopped rapidly. The black hole may not be blazing today, but its fingerprints can remain. That is why dead galaxies can feel like old murder scenes. The killer may no longer be active, but the damage is still there. And sometimes the killer is not one thing. It is the environment. A galaxy in deep space can keep receiving gas from the cosmic web, but a galaxy inside a cluster lives in a rough neighborhood. A galaxy cluster is not just a group of galaxies. It is a huge gravitational system filled with dark matter, hot gas, and many galaxies moving at high speeds. The space between the galaxies is not empty. It contains extremely hot plasma. When a smaller galaxy moves through that plasma, pressure can strip gas from it. The stars remain. Dark matter remains. But the gas needed for new stars gets pushed out. This process can leave long trails behind galaxies. It can turn living galaxies into fading ones. It can create systems that still have old stars but no fuel to renew themselves. This is environmental death. Not a black hole killing from the inside, but the cluster killing from the outside. The galaxy falls into a massive system, and its fuel gets stolen. Over time, its blue stars die. Its bright star-forming regions fade. Its color becomes redder. Its spiral pattern may become less active, and the galaxy slowly joins a quiet population. This kind of death is slower and less dramatic than a quasar blast, but it may be common. The universe does not always kill with explosions. Sometimes it kills by pressure. Sometimes by starvation. Sometimes by cutting off a supply. Starvation may be one of the quietest deaths of all. A galaxy can continue forming stars only if it has access to enough fresh gas. Some gas is recycled from dying stars, but over cosmic time, fresh inflow matters. If a galaxy is cut off from new supply, its star formation rate can slowly fall. It uses what remains. It does not replace it. The star-forming clouds shrink. The bright blue stars disappear. The galaxy becomes quiet. Nothing needs to explode. No central monster needs to roar. The galaxy simply runs out of future. That is what makes dead galaxies so powerful as a metaphor. But we do not need to fake the science to make it dramatic. The real science is already dramatic, because a dead galaxy can be full of stars and still be starving. It can contain gas and still be unable to use it. It can have a giant black hole and still look calm. It can sit inside a massive dark matter halo and still fail to make new light. It can grow through mergers and still remain old. It can evolve without becoming young again. That is the difference between growth and renewal. A dead galaxy can grow by eating smaller galaxies. But if those mergers are dry, meaning they bring little cold gas, they do not restart major star formation. They only add old stars to old stars. The galaxy becomes larger. Its outer halo expands. Its mass increases. But its stellar population remains mostly ancient. It becomes bigger without becoming alive. This matters for giant elliptical galaxies. Many of them may have formed dense cores early. Then, over billions of years, they grew by swallowing smaller galaxies. The core may be the oldest part. The outskirts may be built from stolen stars. The galaxy looks like one smooth object, but it is actually a layered history. A central ancient body. Outer shells from mergers. Globular clusters from different origins. Tidal streams from recent victims. A supermassive black hole in the center. A dark matter halo around everything. A hot atmosphere gas. And very little new star formation. That is what may be hiding inside dead galaxies. Not one dead body. An entire graveyard built from many dead systems. Some of the stars inside a giant dead galaxy may not have been born there. They may have belonged to smaller galaxies that were torn apart. Their original homes disappeared. Their stars were absorbed. Over time, the evidence blurred into the larger galaxy. But with deep enough observations, astronomers can sometimes find the traces: faint streams, shells, ripples, extended halos. These are the remains of galactic cannibalism. A dead galaxy may look peaceful because the violence is old, but the outskirts remember. Gravity does not erase everything at once. It stretches the evidence. It thins it. It spreads it across enormous distances. But the trace can remain. This is one of the most important hidden truths. Dead galaxies are not always born dead. Many are built through violence. The smooth red shape is a final mask. Behind the mask is a history of collisions, mergers, stripping, heating, starvation, and black hole feedback. The universe makes calm-looking things out of chaos. Now think about what would happen if we could fly through one of these galaxies. From the outside, it would not look like the Milky Way. There may be no grand spiral arms, no bright lanes of blue young stars, no huge pink nebulae glowing with fresh star birth. Instead, the galaxy may look like a giant cloud of old light, a reddish-golden haze, smooth from a distance, but full of stars when you enter it. The stars would not be packed together like grains of sand. Space would still be mostly empty. Even inside a galaxy, distances between stars are enormous. But compared with intergalactic space, this region would be rich with gravity. Stars would move on different paths. Some would orbit in random directions. Some would belong to old structures. Some would be part of clusters. Some would be remnants of long-destroyed galaxies. There would be red giants, long-lived red dwarfs, white dwarfs slowly cooling, neutron stars spinning silently, black holes that cannot be seen unless something feeds them. There would be planets around some stars, though from far away, we cannot map them the way we map planets near our own sun. There would be old planetary systems, old debris, old dust, and old chemistry. The galaxy would not feel like a clean grave. It would feel like an ancient city with no new construction. The old buildings still stand. The roads still exist. The archives are still full. But no new generation is building the next district. That is the emotional core of the video. A dead galaxy is not empty. It is old, and old things hide memory. One of those memories is chemical. Every element heavier than hydrogen and helium tells a story. The early universe began mostly with hydrogen, helium, and a little lithium. The heavier elements came later. Stars made them. Supernovae spread them. Neutron star mergers made some of the heaviest elements. Over generations, galaxies became chemically richer. So when astronomers study the stars in a dead galaxy, they can measure chemical fingerprints. These fingerprints reveal how quickly the galaxy enriched itself. If the galaxy formed stars over a long time, different types of supernovae had time to contribute different elements. If the galaxy formed stars in a short burst and then stopped, the chemical pattern may look different. That pattern becomes a record of speed. The atoms inside the stars become a timer. This is why dead galaxies are sometimes easier to study than active ones. In a living galaxy, the story is still being written. Young stars, dust, gas, and active regions can make interpretation messy. In a dead galaxy, the main burst is over. The remaining stars are like a completed archive. They may reveal a short, violent formation period. They may reveal old ages. They may reveal merger history. They may reveal how quickly the galaxy stopped. This is not guessing. This is cosmic archaeology. A telescope is not just taking pictures. It is reading ruins. The James Webb Space Telescope has made this archaeology more powerful because it can observe ancient galaxies in infrared light. The universe is expanding, so light from very distant galaxies gets stretched. Ultraviolet and visible light from the early universe can reach us as infrared. Webb was built to see this kind of light. That means Webb can study galaxies from periods that were much harder to observe before. And that is where dead galaxies become shocking. If Webb confirms a galaxy was already quiescent when the universe was only around 1 or 2 billion years old, then that galaxy stars formed even earlier. It means the galaxy had to assemble quickly. It means it had to shut down quickly. And it means whatever killed it operated early. Black hole feedback, gas exhaustion, environmental effects, or some combination had to happen faster than expected. This is why early dead galaxies are not just another discovery. They are pressure points in cosmology. They test whether our simulations can build galaxies correctly. They test whether feedback models are strong enough. They test whether early black holes grew fast enough. They test whether star formation in the early universe was more efficient than we thought. And sometimes the simulations struggle. That does not mean science collapses. It means the details need work. And that is exactly where progress happens. A good mystery is not when we know nothing. A good mystery is when we know enough to realize something is wrong. Dead galaxies give us that feeling. They are not random. They fit many parts of galaxy evolution, but they appear too early, too massive, too mature, or too quiet in ways that force better explanations. That is why they matter. They show us where the universe moved faster than our imagination. Now, inside these dead galaxies, there's another hidden population that viewers often forget: stellar remnants. A living galaxy is famous for stars being born. A dead galaxy is filled with stars that are aging or already dead. A white dwarf is the exposed core of a star that was once more like the sun. It no longer fuses hydrogen in its core. It slowly cools over time. A dead galaxy full of old stars should contain huge numbers of white dwarfs. They are faint, but they are everywhere in old stellar populations. Some may exist alone. Some may exist in binary systems. In the right conditions, a white dwarf in a binary system can trigger a Type Ia supernova. That means even a dead galaxy can still produce a brilliant explosion. No new massive stars are needed. The explosion can come from old stellar remains. So the dead galaxy can still flash with sudden violence. Not because it is young, because its old corpses are unstable. That is a great line for the script. The galaxy is dead, but the dead stars inside it can still explode. Neutron stars are even more extreme. They are the crushed cores of massive stars. A neutron star can pack more mass than the sun into a sphere about the size of a city. Some spin rapidly. Some produce beams of radiation. Some have intense magnetic fields. And if two neutron stars merge, they can produce gravitational waves and heavy elements. Dead galaxies can host compact eject mergers. These events may be rare, but they prove that old stellar systems still contain active physics. The galaxy may no longer be making many new stars, but the remains of old stars are still interacting. White dwarfs can explode. Neutron stars can merge. Black holes can collide. Binaries can exchange mass. Stars can be disrupted by the central supermassive black hole. The dead galaxy is quiet only when compared with a star-forming galaxy. On deeper timescales, it is full of delayed disasters. This is one of the best ways to make the audience understand the difference between quiet and empty. Quiet means fewer bright young regions. Empty means nothing is there. Dead galaxies are quiet. They are not empty. And the most dangerous quiet object is the supermassive black hole. At the center of many massive galaxies sits a black hole millions or billions of times the mass of the sun. In some dead galaxies, the black hole may be asleep, but sleep in astrophysics only means it is not feeding strongly right now. It still has gravity. It still shapes the motion of stars nearby. It may still occasionally tear apart a star. If gas reaches it, it may wake again. If a merger delivers new material to the center, it may become active. If two galaxies merge, their central black holes may eventually form a binary and merge too. That means a dead galaxy can hide future gravitational wave events. It can hide dormant activity. It can hide a monster that once helped shut it down. There is something almost frightening about a quiet supermassive black hole. An active quasar announces itself across the universe. It shines. It burns. It overwhelms its host. But a dormant black hole is a buried engine. You only know it is there because the stars around it move too fast, or because a flare appears, or because old gas structures reveal past outbursts. It is not gone. It is waiting for fuel. A dead galaxy is one of the best places to imagine that kind of silence. No dramatic disk, no bright quasar, just an old galaxy, red and calm, with a collapsed object at the center that could outweigh millions or billions of suns. And that black hole may be connected to why the galaxy died in the first place. But here is the twist. Black holes may not only stop stars. Under some conditions, they may help start them. Jets from black holes can compress gas. Shock waves can squeeze clouds. In certain environments, this can trigger star formation. So a black hole is not simply a destroyer. It is a regulator. The same type of engine can create or suppress star formation, depending on the galaxy's gas, environment, and timing. This makes the story deeper. The black hole is not evil. It is powerful. And power in a galaxy does not care about human categories. It can build. It can destroy. It can regulate. It can starve. In dead galaxies, the long-term result often appears to be suppression. The black hole helps keep gas hot. It prevents cooling. It maintains silence. But the universe is messy enough that the same physics can play different roles in different places. That is why we do not reduce the script to one villain. We make the black hole the central suspect, not the only suspect. Another thing hiding inside dead galaxies is hot gas that refuses to become stars. This is one of the strangest ideas for normal viewers. People think gas means star formation, but not all gas is useful. Cold gas can collapse. Hot gas resists collapse. If a galaxy is surrounded by a halo of gas at millions of degrees, that gas can shine in X-rays but fail to form stars. It is fuel in the wrong form. It is like having water vapor when you need ice bricks. The material exists, but it cannot build the structure. In massive galaxies and clusters, hot gas can be everywhere. The question is why it does not cool. In some systems, black hole jets appear to act like a heating system. Gas cools and begins to fall inward. The black hole feeds. The black hole releases jets. The jets heat the gas and stop more cooling. This creates a feedback loop. The galaxy tries to restart. The black hole pushes it back into silence. It is a cosmic thermostat. Not perfect, not gentle, but effective. This is one of the deepest reasons massive dead galaxies can stay dead. It is not enough to kill star formation once. A galaxy has to prevent star formation from coming back. The maintenance of death is harder than the death itself, because old stars return gas to space. Mergers can bring material. Hot gas can cool. Fresh inflow can arrive. The universe keeps offering chances. But if feedback keeps blocking those chances, the galaxy stays quiet. That is what makes these systems feel almost locked. The door to new star formation is not just closed. It is guarded. Now, beyond the stars and gas, dead galaxies hide something even larger. Their dark matter halos. A galaxy is not only what shines. The visible stars are only part of the mass. Dark matter surrounds galaxies in huge halos. It does not emit light. It does not glow in telescope images. But its gravity matters. It helps hold galaxies together. It affects rotation. It affects lensing. It affects how galaxies form and merge. A dead galaxy may look like a red island of old stars, but that visible island is embedded inside a much larger invisible ocean. The dark matter halo can extend far beyond the stellar body. It can contain satellite galaxies. It can merge with other halos. It can help draw on material. It can shape the galaxy's environment. So when we ask what is hiding inside dead galaxies, the largest hidden answer is not inside the visible galaxy at all. It is around it, an invisible structure holding the system together. Most of the galaxy's gravitational story may be dark. This is why images are misleading. A telescope image shows light, but galaxies are not made only of light. The dark matter halo is the silent architecture. The stars are the decorated rooms. And in a dead galaxy, those rooms are old, but the architecture still stands. Dark matter also connects dead galaxies to gravitational lensing. A massive dead galaxy can bend light from a more distant galaxy behind it. This creates arcs, rings, or magnified images. In that moment, the dead galaxy becomes a natural telescope. It helps us see farther. Its gravity reveals hidden background objects. Its dark matter helps shape the lens. That means a dead galaxy can help astronomers study younger galaxies behind it. Think about that. A dead galaxy, no longer forming many stars, can still help us see star-forming galaxies from the early universe. It is dead, but its gravity is useful. Its light is old, but its mass is active. It becomes both fossil and tool. That is one of the most beautiful contradictions in astronomy. The universe recycles even silence into discovery. Now let's talk about globular clusters. These objects are some of the oldest residents of galaxies. They are dense balls of stars, often ancient, orbiting around a galaxy. A giant dead galaxy may have thousands of them. Some formed with the galaxy. Some may have been stolen from smaller galaxies during mergers. Globular clusters are valuable because they are old and relatively simple, compared with messy star-forming regions. Their stars can reveal early chemical conditions. Their motions can reveal the galaxy's gravitational field. Their numbers and types can reveal merger history. In a dead galaxy, globular clusters are like old witnesses who survived every disaster. The starburst ended. The gas disappeared. The black hole slept. The galaxy swallowed smaller systems. But the clusters remained. They orbit like fossils. Some may be almost as old as the galaxy itself. Others may have come from victims the galaxy consumed. This makes dead galaxies feel like archives again. Not one archive, many archives. The main stellar body, the central black hole, the hot gas, the dark matter halo, the globular cluster system, the stellar streams, the chemical composition. Every component stores part of the past. The challenge is reading them together. A dead galaxy does not speak in one language. It speaks in light, gravity, chemistry, motion, and temperature. This is why astronomers need many telescopes. No single instrument sees the whole truth. Optical telescopes show stars. Infrared telescopes reveal old stellar populations and dust-hidden regions. Radio telescopes trace cold gas and jets. X-ray telescopes reveal hot gas and energetic black hole activity. Gravitational lensing reveals mass. Spectroscopy reveals chemistry and star formation history. The dead galaxy must be interrogated from every direction. Only then does the smooth red object become a full story. And sometimes that full story includes something unexpected: rejuvenation. A dead galaxy can sometimes restart star formation. Not always. Not easily, but it can happen. If a dead galaxy accretes a gas-rich smaller galaxy, it may gain cold gas. If that gas settles and cools, new stars can form. If an interaction compresses gas in the right way, a small burst of star formation can appear. This means death is not always final. In astronomy, dead is not biological death. It is a state of low star formation. That state can change if conditions change. But massive dead galaxies are hard to revive. Their hot halos, black hole feedback, and deep gravitational wells can prevent cold gas from surviving. They may eat a small gas-rich galaxy and still fail to create much new star formation. The gas may be heated. It may be stripped. It may be driven to the center and feed the black hole instead. The comeback fails. So the galaxy can receive fuel and still remain dead. This is where the story becomes darker. Some galaxies do not lack material completely. They lack the conditions for renewal. That is a stronger idea than emptiness. A dead galaxy can be surrounded by matter and still be unable to use it. It can swallow smaller galaxies and still not become young. It can grow larger and still become older in character. It can have more stars and less future. This is a cosmic warning against judging life by size. A giant galaxy is not necessarily alive. A smaller galaxy with cold gas may be more alive than a massive elliptical with 1 trillion old stars. Life, in the galactic sense, means formation. It means gas becoming stars. It means new light appearing. Without that, the galaxy becomes a monument. Huge, powerful, beautiful, but no longer creative. Now we bring the Milky Way back into the story. Because dead galaxies are not only distant mysteries, they are possible futures. The Milky Way is alive today. It forms stars. It has cold gas. It has spiral arms. It has nebulae where new stars are born. It has young blue stars and old red stars. It has a central black hole, Sagittarius A star, which is quiet compared with active galactic nuclei. But the Milky Way is not isolated forever. Andromeda is moving toward us. Over several billion years, the Milky Way and Andromeda are expected to merge. This merger will reshape both galaxies. The night sky, if anyone is around to see it, would change dramatically. The galaxies would pass through each other. Gravity would stretch stars into streams. Gas clouds would interact. Some star formation could be triggered. The central black holes may eventually move toward the center of the merged remnant. Over very long timescales, the final galaxy may become more elliptical-like. The Milky Way's spiral structure may be destroyed. The galaxy we know may become part of a larger, older system. Maybe not immediately dead. Maybe not completely quiet at first. But over time, star formation will decline. Gas will be used, heated, or expelled. The remnant may become redder and quieter. Our galaxy's future may resemble the dead galaxies we observe today. That changes emotional weight. We are not studying strangers. We are studying a possible ending. The Milky Way may one day become a fossil galaxy too. Its spiral arms gone. Its blue star-forming regions faded. Its central black hole. The universe does not turn off suddenly. It fades. Dead galaxies are early examples of that fading. They are places where the future arrived early. Inside them, we see a preview of a universe where old stars dominate, remnants accumulate, and new star birth becomes rare. That is why dead galaxies are not just about galaxy evolution. They are about cosmic destiny. They show us that the universe has an aging process. It was once hot, dense, and simple. It formed the first atoms, then the first stars, then the first galaxies, then massive galaxies, then black holes and clusters and heavy elements and planets. For billions of years, it built complexity, but complexity depends on fuel. And fuel is not infinite in the form needed for new stars. The universe can recycle some material, but expansion, heating, feedback, and structure formation all affect what can collapse and what cannot. Dead galaxies are places where the cycle has already slowed or broken. They are not the end of the universe, but they are local endings, small versions of the larger fade. Now the script should move toward its final emotional and scientific conclusion. What is hiding inside dead galaxies? The answer has changed from a simple list into a layered idea. At first, we thought the answer might be old stars. Then we found stellar corpses. Then globular clusters. Then hot gas. Then dust. Then dark matter. Then black holes. Then merger scars. Then chemical memory. Then early universe problems. Then possible futures. But the deepest answer is this. Dead galaxies hide the proof that the universe is not only creative, it is selective. Not every galaxy keeps growing forever. Not every star-forming system remains alive. Not every supply of gas becomes new stars. There are forces that build galaxies and forces that stop them. Gravity pulls matter together. Gas cools. Stars form, but feedback pushes back. Black holes heat gas. Supernovae stir it. Clusters strip it. Hot halos prevent it from cooling. Mergers reshape it. Dark matter holds a stage, but ordinary matter decides whether light is born. A galaxy lives in the tension between these forces. When creation wins, stars form. When suppression wins, the galaxy dies. A dead galaxy is a result of suppression winning for a very long time, and yet it is still beautiful. This is important. Dead galaxies are not failures in a human sense. They are not mistakes. They are natural outcomes of cosmic evolution. A giant elliptical galaxy can be one of the most massive, ancient, and important systems in the universe. It can anchor a cluster. It can contain a huge black hole. It can lens background galaxies. It can preserve the memory of early star formation. It can host old stars and ancient clusters. It can be scientifically priceless. Dead does not mean worthless. Dead means no longer forming new stars in a major way. The value is in the record. The galaxy is not a nursery anymore. It is an archive, and archives matter. Because without dead galaxies, we would not understand how galaxies shut down. We would not understand the role of black holes in regulating star formation. We would not understand how massive ellipticals grew. We would not understand how early the universe could build mature systems. We would not understand the long-term fate of galaxies like our own. The dead galaxies are telling us what the living ones may become. They are not the opposite of life. They are the next chapter after a certain kind of life ends. Now imagine the final visual of the video. A telescope image of a red elliptical galaxy. At first, It looks calm, almost boring. No bright spiral arms. No colorful star-forming clouds. No dramatic explosion. Just a soft red glow in deep space. But now the viewer knows better. Inside that glow are billions or trillions of old stars. There are white dwarfs cooling like embers. There are neutron stars with impossible density. There are black holes hidden in darkness. There are globular clusters older than Earth. There are chemical fingerprints from ancient supernovae. There are faint streams from galaxies that were swallowed. There is hot gas that cannot become stars. There is dark matter holding everything together. There may be a supermassive black hole at the center, quiet now, but powerful enough to have shaped the galaxy's fate. And there is a missing ingredient. Cold gas, the one thing needed to make the galaxy young again. That absence is the heart of the mystery. A dead galaxy is defined as much by what it lacks as by what it contains. It contains stars, remnants, black holes, gas, dust, dark matter, and memory. But it lacks renewal. That is why it feels dead. Not because nothing is there, because the future has gone quiet. And when Webb looks at dead galaxies in the early universe, the mystery becomes sharper, because those galaxies did not wait billions and billions of years to become quiet. Some shut down early. They formed fast, grew fast, and stopped fast. They are cosmic evidence that the early universe was not slow. It could build giants quickly. It could create black holes quickly. It could enrich galaxies quickly. And it could kill star formation quickly. That means the universe's childhood was more intense than we imagined. Less gentle, less gradual, more violent, more efficient, more surprising. Dead galaxies are not just old objects at the end of time. Some are young universe fossils. They are evidence that cosmic death began early. While other galaxies were still blazing with new stars, these systems had already gone quiet. That is what makes them haunting. They are not the universe after the party. They are locked rooms found while the party is still happening. And inside those rooms, the lights are already off. The final question is whether the silence is permanent. For some galaxies, maybe not. A new gas supply can restart star formation. A merger can bring fuel. A quiet galaxy can experience a small comeback. But for the biggest dead galaxies, the answer may be close to yes. Their own structure prevents revival. Their hot halos resist cooling. Their black holes regulate gas. Their environments strip or heat material. Their mergers are often dry. They may continue growing, but mostly by adding old stars. They may keep changing, but not in a way that makes them young again. That is why the word dead still works. It is not perfect, but it captures the loss. A dead galaxy is a system where the great engine of star birth has shut down. The stars still shine. The remnants still wait. The black hole still pulls. The dark matter still holds. But the galaxy's creative age is over. And maybe the most haunting part is that dead galaxies do not look dramatic. They do not always announce their tragedy. They do not explode across the sky. They do not scream like quasars. They fade into red calm. Their violence is buried in history. Their death is written in missing gas, old stars, and quiet spectra. The universe often hides its biggest changes behind silence. That is why astronomers keep studying these galaxies, because silence can be evidence. A galaxy that is not forming stars is telling us something. It is telling us the fuel is gone hot, stripped, or blocked. It is telling us feedback may have won. It is telling us the black hole may have mattered. It is telling us the environment may have changed everything. It is telling us the early universe may have been more extreme than we thought. And it may be telling us something about our own future. The Milky Way is not dead. Not yet. But one day, it may no longer look like the galaxy we know. Its spiral arms may vanish into a larger remnant. Its star formation may slow.